In this video, I will study various examples of pairs of inverse functions. For the theory behind inverse functions, see the previous video. I will begin with a very simple function, the function f defined by the equation f of x equals 2x plus 1. The graph of f is a line. The domain is all the reals, the range is all the reals. Everything should work fine for this example. The inverse is defined by this statement. X is f inverse of y if and only if y is f of x. We have an equation for f of x equals 2x plus 1. So I can write y equals 2x plus 1, and then I have to solve for x. In this case it is easy. We get x equals y minus 1 over 2. So I have an equation for the inverse function. F inverse of y equals y minus 1 over 2. If I want to do the same for a different function, the process will always be the same. However, solving for x may be more difficult. Sometimes it is even impossible to solve explicitly. Since the calculations are easy with this particular example, let's use it to verify the identities that we know pairs of inverse functions must satisfy. We know that if I compose a function and its inverse, I should get the identity. Let's check it. If I write f inverse of f of x, first I use the equation for f inverse. I get f of x minus 1 over 2. Then I use the equation for f. I get 2x plus 1 minus 1 over 2. And yes, this simplifies to x. Now let's compose the other way around. If I write f of f inverse of y, first I use the equation for f. I get 2f inverse of y plus 1. Then I use the equation for f inverse. I get 2 times y minus 1 over 2 plus 1. And yes, this is y, as it should. For my second example, let's look at a classic, the exponential function and the natural logarithm function. This is not an example of computing an inverse, but rather of how to define a new function as an inverse. The exponential and logarithm are inverses of each other. They satisfy the definition of a pair of inverse functions. More than that, this statement can be used to define one of them if we already know the other. You probably did this in high school. You took the exponential as a starting point, assumed you already knew what an exponential was and its properties, and then you used this statement to define the logarithm. But it can also be done backwards. In analysis, when we try to define everything rigorously from scratch, it is common to start with the logarithm. The logarithm can be constructed as an integral without assuming anything. And then we use this property to define the exponential instead. Let's look at their graphs. We see that the domain of the exponential is all the reals, which is the range of the logarithm. And the domain of the logarithm is the positive reals, which is the range of the exponential, as it should be. Notice that one graph is the reflection of the other with respect to the diagonal of the first and third quadrants. This always happens with pairs of inverse functions. Switching from a function to its inverse means swapping the roles of x and y. Now think of swapping the x-axis and the y-axis. It is the same as reflecting with respect to the diagonal. That's why graphs of pairs of inverse functions always have this property. Finally, the composition of a function and its inverse should be the identity. Indeed, the logarithm of e to the x is x, for all real numbers x, and e to the logarithm of y is y, for all positive reals y. As a last example, I will look at something more interesting. Consider the function f defined by f of x equals x squared. Here is its graph. We can't quite find an inverse for it. This function is not one-to-one. For example, f of 3 equals f of minus 3, and therefore it does not have an inverse function. However, we can still try to construct something close to an inverse. Here's the graph again. Instead of the full function, I could restrict to a smaller domain and consider only a piece of it. For example, I could keep just the function represented by this piece of the graph in red. Then I am maintaining the full range with smaller domain, and now the new function is 1-to-1, so it will have an inverse. To be clear, this is not the only choice I could have made. I could have chosen this other half of the graph instead. Or, if I get creative, perhaps this. But that could be silly. Instead, let's stick to my original choice. What is the inverse of the function represented by the piece of the graph in red? It is the square root. Indeed, let us call g the function defined by the equation g of x equals root x. G is not the inverse of the function f. G is the inverse of the restriction of the function f to the domain 0, infinity. This is actually how you learned of square roots back in primary school, even though you did not use these words. For example, you learned that there are two real numbers whose square is 9, 3 and minus 3, but that when we write root of 9, we mean the positive, 3. So yes, the square root is the inverse of the restriction of f to a smaller domain. Equivalently, saying that a number a is the square root of a number b means that b is a squared. If I were to stop here, it could mean that f and g were inverses of each other, which they are not. And also that a is positive or 0. But there is more. We know that when we compose a function and its inverse, we should get the identity. This will still be true as long as I stay in the right domain. What is the square root of x squared? It is x, but only if x was positive or 0 to begin with. Otherwise, as you know, it is the absolute value of x. The moral is, if we have a function that is not 1-to-1, we can restrict it to a smaller domain and construct its inverse. But the way we define inverse and the properties of inverse functions will have to be modified accordingly. This will become very important when we define inverse trigonometric functions.